Hello, my name is Lindsay Broadway, and this is Physics 2211, Lab 3, a black hole. So the lab is divided into two parts. The first part is to find the mass of a black hole, and the second part is to find the velocity that a spaceship needs to escape a black hole without running into the planet that orbits it. The principles that are used here are Newton's second law and the universal gravitational force. My results are these, but I will get into those later. So more on these principles and formulas. Newton's second law is defined as F net is equal to the change in momentum over the change in time, which you can use to find the velocity update formula, which is below, and then finally the position update formula. And then another key aspect is the components of net force. So the parallel and perpendicular components added together equal the total net force. And finally, the formula for the universal force of gravitation is negative g, which is 6.7 times 10 to the 11th times mass of one object times the mass of the second object divided by the magnitude of the distance between the objects squared times the unit vector of the distance between the objects. So the first part is the mass of the black hole. So the system is the star and the surroundings are the black hole. The initial conditions are the mass of the star that was given to us in the lab instructions and delta T, which I found by the number of seconds in a day. And then on the right, you can see a free body diagram of the black hole and the star and the forces acting between the two, which are the force of gravity, which are equal and opposite. So the model that I used here, I made total mass and counter variables. I initialized those at the beginning, but those will come into play later. And then I used the momentum formula to find the initial and final momentum. And then I use delta V and delta P, which is change in velocity and change in momentum. And I use those to find the net force, which is dP over dt. Finally, I use the parallel and perpendicular components of the change in momentum to find the net force. And then the mass of the black hole is defined as the magnitude of the net force times the magnitude of the star's position squared divided by the universal gravitational constant times the mass of the star. And then I updated the total mass by adding the mass of the black hole every iteration. And then at the bottom, I found the average mass by dividing that total mass by the counter, which I updated. And then in the middle, these are just me using scalars to find the arrows for the net forces for perpendicular and parallel components. Finally, the mass of the black hole was found to be 7.37137 times 10 to the 33 kilograms. So how are the net force and the change in momentum different? They're the same. Net force is equal to the rate of change of momentum given by Newton's second law that F net is equal to dP over dt. Some sources of error for this lab could be rounding during each iteration, which would impact the final result for the mass of the black hole. The second part of this lab is to find the velocity to escape from a black hole without hitting the planet that orbits the black hole. So the system is the star and the planet, and the surroundings are the black hole. Some initial conditions are the mass of the planet and the mass of the ship that are given to us, and then the ship speed, which I found through trial and error. So the model I used to find the force of the black hole on the planet using the force of universal gravitation. And then I also did the same thing to find the force of the ship on the planet and then added those two together to find the net forces on the planet. And then the second part, I did the same thing, but I did each surrounding black hole and planet to find the forces on the ship. Finally, I used the position and velocity update formulas here to update the velocities and positions for both the planet and the ship. And you can see this through my model. And I eventually found that the velocity was going to be -3 times 10 to the 7, 2.5 times 10 to the 6 meters per second. So what initial velocity would your spaceship need to have in order to enter into an orbit around the black hole without crashing into the black hole or the planet? So through trial and error, I found that the velocity would have to be negative 1.55 times 10 to the 6, 1.55 times 10 to the 7 meters per second. And you can see my model on the right, which was finished after 90 minutes. Some sources of error in this part of the lab would be rounding in each iteration and also an incorrect initial mass for the black hole. Thank you.